Okay, so I think we should still have at least 20 students. Okay, so we'll wait for 2 minutes. Okay. But take it this time. So last time, I think some students still have some question about, this slide, right? So uh, because we are still waiting for maybe more than 10 students, if you have any question, can you ask? Then I can answer you according to your question regarding this question. So I have a one-on-one meeting with some students. Seems that the students didn't exactly get what this question is about earlier. Yeah, if you have any question, just let me know. Okay. So just a recap, maybe quickly, just in case some students still didn't understand this. So these are not network ID. These are all IP address. This is a range of IP address. Okay. These are binary IP address. And our last question, for example, here asks you to change the decimal. Otherwise, it's a binary. Okay. And because in the forwarding table, you can only say, hey, have a prefix. For example, here, the prefix, you share the prefix to one is this. So you can have something like 111000000, right? And additionally to this, these are the shared prefix. Okay, whatever fall in this should and a dash 10, right? Because it's 8 plus 2. Okay, goes to port 0, something like this. Yeah. Okay, and you have to have one entry. Right? The prefix should be a common prefix. Okay, similarly here you can go to Q. Right? And this is really the case because it's in the host the segment, right? So it's all range, right? From 000 to 111. Okay, all range. And the only tricky thing is, for example, the third range 2, right? The third range 2, your common prefix is here because this bit is different. Okay. Then we have another entry, right? So we have one entry that is this thing, okay, 1110000 and 2 bytes basically, 16, right? And goes to 1, right? And we have another entry, which is 7, right? Because the last bit is not considered, okay? Which goes to 2, right? So will we be in trouble? Let's say if we see something like, this prefix, 7 bits, is also shared by this, right? But we are not in trouble because we have 16 bits here, right? So if you happen to fall into this range, okay, which is the 1th range, right? Then you will go, this one will be active because this is longer. And this range exactly, you see the last value of the 1th range plus 1. Okay? The 111, this is 100. Okay? So smaller than the beginning value of second 2 will all go to second 1. Okay? Will go to port 1. Okay? And larger than there's something that is tricky. So I see some chat. Okay, yeah, so some chat asked me to talk about it again. So for the larger side, you see that if you think about it, right, so this prefix, okay, does not include all 111, okay? Which means, for example, if you look at this one, 10, right, it's outside tooth range, okay, because tooth range are most to 0, okay? So how do you represent this? Basically, you have another item, for example, you say, hey, if we start from this prefix, we should go to 3, right? So it's not difficult to see that, this is last range that this can be 0. If you plus 1, this becomes 1, 0, 0, 0. So basically, as long as you start from 1, so 1, 1, 0, 0, 0, 1, 1, okay, it should go to 3. But that doesn't answer all the questions, right? So for example, if you this basically because you are in this range. If you are outside this range, let's say you have 1, 1, 1, 1, right? Okay, or if you have 0, 0, 0, right? So they should also go to 3 because it's the other one. Okay, so we have 5 entries, 2 entries for 3. Okay, so you have 5 points here. Yeah, so Ideal. So can you explain what is larger than in your question?
The otherwise on link 3.
Okay, in link 3. Yeah, just a moment. Let me go clear. See, otherwise means if it's not within these 3 ranges. So, if it's not within these 3 ranges, right? So so you have this range, okay, this range, this range. If you are not within this range, you go to link 3. Okay, it's the otherwise means. You answer your question? And these are the 2 numbers, right? Let's say this is A, this is B, right? So here, anything smaller than A, X to B should go to property. Okay? This is what
Yes.
yeah.
Any other question? Thank
you. Yeah, you're welcome. All right, so I think there's no more questions. Again, so it's pretty clear how to answer this question. Right? So, but the details, a complete solution, you need to work out yourself. Okay. And the midterm will be some multiple choice, some will be the fill in blank, some will be this kind of answering questions. Okay, so only multiple choice and some very simple number that you fill in will be auto graded. Okay, all the other questions will be graded by T. I hope I answered that question. And yeah, let's go back to the. Let's go back to where we were last time. Okay, I think we need to quickly go through this slide because of the time limit. We will not be able to go to every details, but everything that we will test, there's a guarantee that we will be in this slide. Okay, so do prepare the slide well. Whatever you don't understand, try to comprehend it. Okay, so this first layer for physical layer, right? So for physical layer, we have like these kind of cable optics, those kind of thing, right? So basically, that's how you transmit bits. This is the physical layer stuff. Okay, and then we have the second layer. So when we talk about layer, it's really one means we are using bottom-up solution. If the first layer is physical layer, not application. And then we have the data link layer. And so data link layer, actually, we have the framing concept. Right? You want to have bits into packets. Okay, and we have the MAC address, which is 48-bit. Right, so and for framing, we have 3 ways of doing framing. So we have byte-oriented, bit-oriented, and clock-oriented. Right? And byte-oriented means everything is in the byte. Okay. But what if this ending byte is also in the middle? Right? So what you should not end here. Okay, you should end right here. Okay. So in order to avoid this from happening, you need to have a data links escape (DLE). Okay. So if you see DLE in our question, right? So I already remember. Okay, so if you see DLE in our question, this is talking about this slide. We don't just get confused. Okay. Right. So and even if you have DLE, any special token, you should do an escape, meaning this part of the data. Okay. So this is one method. The second method is you can just say, hey, there are so many bytes, right? So and then no matter how many, what's inside, what's the content, you don't care. You just go to the end of this number of bytes. Okay. So that's another way to replace the DLE. Okay. So both methods are byte oriented. This method called byte counting that we have put in the beginning. And there's also another method, right? We have 3 methods. Another one bits oriented. Okay. So basically, we make sure because we have the setting nodes, right? So these are called setting nodes. Okay. And the setting nodes means where we decimate the frames. Okay. So delineate the frames. So basically, if you look at the setting node, we have 6 ones. Right? So whenever in your data you see 5 ones, you will automatically insert a 0. Okay. So that's why we have 20% overhead. Right? So only when in the setting node you will see 6-bit. Right? So this is the so-called bit stuffing. So you have your overhead is much smaller. Right? If you actually it's not smaller, but whenever you see 5 ones, you need to add 0. Okay, if you have lots of ones, it's 20%. But if you don't have a lot of consecutive ones, that's not. And so you don't insert a lot of bits. Okay. And the third method is called clock-based framing. Okay, like you saw now, this is really for optical networks, like very high bandwidth. And because everyone has a clock, then you can align easily. Okay, so that's no longer a big problem. So yeah, so this is low-level details. And then after we know how to delineate the boundaries, right? So delineate the frames, the bits into frames. Okay. The next question is how to make sure the string of bits are sent correctly. Right? So if you have, let's say, 7-bit ASCII characters, right? And you will add another bit, make sure there are only even number of bits, 1, 1, 1, 3, 4. Okay. So this is how you do. This is called a parity bits, right? And this can detect 1-bit error because if you have 1 bit flipped, then the number of ones will not match. Okay. And it's not reliable against the birthday errors. Let's say you have 2 bits flipped, then you cannot detect them because it's flipped back. Okay, it's odd, even, or you have 4 bits, a string of 4 bits. So it's birthday. Okay, then you cannot detect it. I see a question in the chat. Okay. Oh, so there's a extended lab assignment. Okay, can you send me email? I will figure it out. Okay, if it's the deadline in that case, I can talk to the TA to extend to early next week. Okay, but just send me email. Okay, remind me. And so that's a two-dimensional parity, right? So which means you have a stream of bits, right? You can make them 7 bits in a row and then just like this. Okay? And then you can have rows and columns being parity. Okay? This bit must be the parity of this marginal column or marginal row. Okay? It's basically the parity of the sum because each one is like the sum. Of course, it's always covering. 1 plus 1, 0 plus 1 again. So it's basically the summation, but only 1 bit. Okay. And using this, you can actually detect, you can detect 3-bit error for sure. Okay, some more bits can be detected, but that special case you cannot detect 4-bit error. For example, if you look at these, right, so this column will be detected. Okay, if you have this, then this row will be detected. But if you have 4 bits, you cannot detect. Okay, because each row and each column are flipped twice. Okay, so so you can detect using 2-dimensional parity. You can detect at least 3-bit error. Okay, and we can even fix 1-bit error because if you just have 1-bit error, then you know exactly which row and which column mistake happened. Right, so we can locate this bit and flip it. Okay, so we can fix 1-bit error and detect 3-bit errors. Okay, at least some 4-bit error you can also do. Let's say you can even detect 8-bit error. Let's say if this error in the same row, but every column you can detect. Okay? But up to 3, you have a guarantee. Starting from 4, you don't have that guarantee. Okay? Maybe in some cases you cannot find that this. And feel free to ask anytime you have questions, okay? Because this is important stuff. Right? And we talked about checksum. Checksum is really, you make this frame into 16-bit units, right? Like a 2-byte unit, okay? And then you make some summing up, okay? And finally you get a sum, and you put the sum as this checksum field, right? And when you get this data frame, right? So you also every 16-bit you get you have a 2 bytes, right? And you add those 2 bytes together and you get a sum, and then check whether it's the same as the checksum. Okay, if it's the same, then there's no error. And there may be error flipped twice, but you don't think there's error. If the checksum doesn't match, some bit is flipped, you will drop it. Okay, maybe a retransmission message. So this checksum, if you remember IPv4, you still have checksum. IPv6 will remove it. Okay, and later if you look at the TCP/UDP, you will also see the checksum field there. So this is basically a summation. But if you have the same bit flipped, right, so the sum, let's say 0 plus 1 and the 1 plus 0, right, it's still 1. Okay, so you cannot detect the difference. And there's a CRC solution, right? It can, we didn't go into the details, so we will not pass through the details. Actually, this is like the like 2 years ago when I teach this course, there's a question very intensive on this. And now we just make it simple. Okay, so all you need to know is that it's based on the field theory. Okay, field it's a group theory, field theory. So this kind of concept. Okay, algebra. So and then you have So the nice thing about it is that firstly it has fixed overhead preference, just like the checksum. Okay, and it's quick to implement. But another thing that only 1 in 2 to the power of 32 chance you will miss a number, which means the error detection will be way higher than checksum. Okay, so this is, but there's some confusion involved based on field theory. If you have interest, I highly encourage you to check it out. But we will not test you on the details. Okay? But again, so if you have 1 bit error, right? So so probably will not detect this variable. The reason is because it's based on division, right? So if you division modulo and you get the same number, the probability is very low. Okay, exactly add that amount of number. Right? It's like a round of that, right? Then the modulo value is the same. It's kind of based on that kind of concept, but you can check in the details. So then we have, because we are still in the data link layer, if you look at it, right? So we have media access, right? So we have 3 strategies you need to know. The first is called a channel partition. Right? So we talked about, there's TDMA, time division. Everyone has a slot to set, okay? And if you have 100 users, you have like a sliding window of 100 slots, one for each user, right? In every window, you can only send in your slot, okay? The frequency is like a vertical, right? So you can only send in this frequency band, another user can send at another frequency, right? Even though user can send together, but your bandwidth is low. Right? So time division, you can use the whole bandwidth, okay? The whole frequency bandwidth is low. And then not much difference there. Okay, so and because when the peak speed you can send frequency is low. Okay, so you cannot fully utilize all the frequency to send it. And there's also a CDMA, right, code division. But we are not talking about that. So besides partition channels, there's also tick turns, which is the passing tokens. We didn't enter the details of tick turns. And another very, very, very important type of media access is contention based. Okay, aloha this kind of thing. So which means you don't have a designated slot. You can send whenever you want almost. Right? So maybe there's some slot, but you will not wait for a long period of time. Okay. And but because 2 people can talk together, right? 2 hosts can send stuff to the same media, okay, then you need to have a way to recover if there's conflict. Okay. Examples include Ethernet and Wi-Fi, but Wi-Fi, Aloha is more like a Wi-Fi kind of, right? Wireless, and Ethernet is more like CDMA, a CSMA, CSMA CD, and a CSMA CA, okay, MACA. Okay, we will look at those stuff. I think the MACA is for wireless. Okay, so let's take a look at what they are. Right? So you need to be familiarize yourself with these 4 contention-based protocols. Okay? The first is called Aloha, the second is called slotted Aloha. Right? And then we have these 2. Okay? And let's take a look at, so these first 2 are really for the radio network in the early days. Right? So this is for the Ethernet, but Ethernet, not by switch. Right? It's more like a hub, this kind of early day shared media. Okay, and the last one is async Wi-Fi. So, oh no, let me see. No, these 2 are for Wi-Fi is for MACA or CSMA CA. Okay. Both CSMA and CSMA CD are mainly for Ethernet. Okay. Firstly, you need to know Aloha. So if we ask you some question like, no, you can transmit immediately when you want. Anyone can send immediately. So then you probably most likely we're talking about Aloha. Okay? So receivers will acknowledge all packets. Right? So if you send A, right, you want to send, you just send. There's no waiting. Slotted Aloha, you still need to wait for a small slot, okay, at the beginning of the slot. But Aloha, you really stations transmit immediately, okay. And when you transmit to B should acknowledge you, okay. Right. So why? Because there could be a case, for example, both are sending, so you get garbage. You will not get the data, you will not acknowledge A and C, right? Then you know that collision happens. Okay? Then A and C need to wait for a random time to be transferred. Okay? You need to wait for a random time because if you wait for the same amount of time, then A and C will conflict again at B. Okay, so that's aloha code. And it's simple, and so it's a good case really if you only have a few senders. Okay, right? The probability that anyone is sending, yeah, it's two people are sending is very low. Okay? Most of the time, only one person they want to send, they can only send. If everyone has something to send, TDMA, FDMA is the best because because you have enough things to send, you will always fully utilize your slot. If all the users are busy sending all the data, that's all they have, then these are actually the best. So here's the trade-off. Right? You need to know that TDMA, each host need to wait for its turn, so that's latency cost. Right? There's a delay, and the delay is still proportional to the host. Right? If you have 100 people, you can only send in, let's say, your slot, and then you need to wait for 99 people slot, and then you send again. If there's some delay, but if you just look at throughput, this is the best. Okay, that's because everyone, if condition on everyone has something to send, then every slot is occupied. In Aloha, no, you can send immediately, so there's no latency, but there's still possible delay, okay, because you can conflict and wait for a random time. But in the ideal case, there's no delay. So, but the utilization rate is very low because a lot of times you just conflict with others. Okay? That's collision. And so Aloha, we don't have any slots, which means let me see. Right, let's fix. Let me take it again. Let's fix this slot. Okay, what's the case that you will not conflict with slot? If you are here or before, you're fine. Okay, you start here or before. If you start to be here, you will have overlap. Okay? But all the way to here, you still have some overlap. Okay? So you need to go to here. So if you look at their distance, this is exactly twice the frame size. Okay, so as long as you overlap with this, in this two slot, right, two frame size location, right, when you start begin to send, you will conflict with the other Aloha frame. Okay, to address this issue, let me see. I think there's a chat question. So yeah, so I think probably I passed this long time ago. Right? So it's maybe you can ask me offline after this, because I just see it, okay? And because on this slide it's not about it. So if you have a question, please mute yourself. Okay, otherwise I may not check the chat all the time. Okay? So this means your utilization rate is 18%, which is half of the other one. Okay, the other one, slotted Aloha because you have the slot. Right? So the difference is that you have to wait to the next slot. Okay, that you can send. But you can only send at the beginning of the slot. If you send in the previous slot, then you have to wait till the beginning of the next slot. Okay. But because your frame can only conflict with another frame in that slot, so your throughput is double. And why it's double like that number? So we put it here. So like we have a proof before, okay, if you remember. So this will kind of double the peak. The peak will be double. Another important concept, right? So we move because after Aloha, right? So these CSMA are based on Ethernet, shared medium. Okay. So for the Ethernet, you have the preamble, okay, and preamble are kind of like this. Okay, so you need to know the Ethernet. You have preamble here. Okay, that's the format. Okay, and then you have different like starting frame, and then you have a MAC address, right, and source and destination address, and you finally have a checksum. Okay, and you have a pad because you have the minimum allowed. minimum allowed Ethernet size. Okay? If you are smaller than that, maybe you will fully send the frame, but then you detect a conflict from the other side. Okay? And so Ethernet is in the old days is the broadcast technology, which means you can have T connector, and when you send, other people will hear. Okay? And for the hub, it's the same. Okay, so you need to know that hub and the T connector, they are physical layer devices. Okay, there's no data link layer handle. Okay, that's why it's just like the physical medium. Okay, like the same piece of work. And then we have, now that we tell you the Ethernet structure, so this is the CSMA-CD used by the old days Ethernet. Right? So the algorithm is that we have so-called carrier sense, which means you will sense the while and see when somebody is sending. Right? And if somebody is sending, you don't send because you don't want a conflict. Until the while becomes idle, then you can send. Okay? And then when you send, while you are sending, you will continue to wait for collision. Okay, it stands for what is a collision. Yeah. So if that is collision happens, that's why it's called CD, collision detection. Okay, if no collision detected after you fully put the frame up to the while, then you are done. It's sent. If there's a collision, then you need to abort immediately. There's no point to continue sending. Okay, it will corrupt the other information. Okay, both actually will abort, right? Because we know that Ethernet frame has a minimum size allowed. Okay, you cannot go beyond that, but below that, okay, because this time is allow you to listen to the other people who talk simultaneously with you, but because of the propagation delay, right, there's some light speed transmission to your side. Okay, right, then you can detect if the other people are talking about, are still talking. Okay, so these are really just kind of that case. And then you need to know that if you collide a board, there's a concept called exponential backup. So which means you need to wait, but if next time you wake up, so let's quickly go to expanded backup. Okay, so firstly for Ethernet expanded backup, you need to know this number, right? So here we put it clearly, 512 bits. Okay, it's a minimum unit. Okay, and so you are sampling, as this is the minimum unit, and you're sampling from a range. Okay, but this range, each unit is like the time you send so many bits. And if you find the next time you sample a range and you find a collision again, you will double this range. Okay, so that's why each time is times 2. This is 2 to the power n. Okay, so there's some other details you can be aware of. Right? So like when you reach 10 times, you don't double again. So the reason we double is because if you try many times, it's still collide. That means a lot of people are talking. You should not continue to send stuff. Right? If a lot of people are busy sending, retrying, then just to get stuck. Okay, everyone's colliding with everyone else. You should wait longer.
What happens between being kept at 10 and dropping the frame at 16? Oh, does that just mean for 11 through 15, it doesn't increase in time anymore? Is that what it means?
It's about this range stay at 10. It's okay?
Okay.
Yeah, 11 is due to the top 10. Yeah, right, so then we have, you need to know this, right? So, the IEEE 802.3 is Ethernet. Okay, 802.11 is Wi-Fi. Okay, these you need to remember these numbers, right? And Ethernet has shared collision domain, also because it's light speed. Okay, but radio, there's some more complications. So that's why we use markup, so CSMA-CA. Okay, so CSMA-CA is a markup plus CSMA, basically. Okay, so we are focused on markup. Okay, so in the wireless environment, you firstly have a hidden terminal problem. I think we should go a little bit faster because half an hour has passed. Okay, so basically we'll collide here, but A and C will not detect A and C are talking with each other because there's a range. Okay, so this is called a hidden terminal. The two people that collide at B cannot detect each other. Okay, there's another concept called exposed terminal problem, which means, hey, even though B and C, if you really detect, you will find, hey, B and C are conflict with each other. But actually, they can be successfully diverged because at A, you can only hear, right? You can only receive the packet from B, not from C, because C cannot reach you. Right? So you should not really rely on carrier sensing, right? So if you do that, like this case, you will just back off, which is not necessary. Okay? So that's why we have another protocol called Maca. Okay, so Maca is basically you have the sense the channel. If there's nobody using it, you will do the RTS, request to send. So it's a soft reserve, which means hey, this host in the sender's range knows it's reserved. Okay, and then but you actually just destination is this receiver, not this host. Okay, the receiver once it's received, it will say clear to send. Okay. Once you say clear to send, which means the sender will send you stuff. Anyone host in your receiver range will know, hey, this receiver is trying to get something. I should not send. Okay, this will be blocked. Okay, so, and then the sender will start to send data. The sender will send it also to here, but it's fine. Right? So that's why it's called soft reserve. Right? It doesn't get a clear, but it should assume it's reserved. Okay? And finally, the receiver will send the acknowledgement when it gets data. And then, then this host can continue to send stuff. Right? Here, you should not send any stuff because this receiver is receiving things. You don't want to conflict. And here, the sender knows it's successful transmission. Right? So you don't need to retransmit. You can safely, you can be safe. Okay. So here, there's still possibility to have collision happen. Right? So because this is CTS is the hard reserve. So here is soft reserve. So there's still possibility of collision. So collision is in Maca. So this will be, for example, a question we're asking. Right? So what if the sender does not receive CTS acknowledgement? Right? So this is the sender. If I don't receive CTS, I don't receive acknowledgement. What will happen? Right. So if that is the case, you time out. You didn't receive anything. Right. So then you need to retransmit. And so you need to assume collision and to back off and retransmit. Because this is possible. Okay, so if you don't get this, maybe maybe the CTA is corrupted by someone else is sending stuff. Okay, so you have to retransmit. And so far we talked about the hub and the T connector, which makes the physical layer. So the hub is physical layer. Okay, so you can also have another concept called bridge. So the hub, if you get here, it's like the same piece of metal, right? So it's just go to the other machine. But here, if you send to B, it will not go to A. So this is a bridge. Right? So the bridge is a data link layer. Okay, data link layer device. So when we ask you this kind of question, which layer is bridge in? Right, it's data link layer. If we ask you which layer is hub in, it should be physical layer. Okay, yeah. And the bridge really each port connects to a shared network, right, subnetwork. Okay, like this. Okay. We have to go a little faster. But you can look in the details yourself. Okay, so the bridge again we want to emphasize it's a data link layer. Okay, it operates at layer 2. Okay, and there's a concept of forwarding table. Right? So whenever you send stuff to this port, you will have an entry. Remember, hey, this port, this machine is sending this Ethernet data frame to this port. Right? So you will automatically remember this into the bridge. The forwarding table. And you will have an age, which means if the time is too long, right, it will time out. Okay, so this is helping you to remove it, just in case any host here at port 1 leaves, right? If this time out, I will remove it. But if you keep sending stuff, this age will be refreshed to 0 again. Then it will not be removed. Okay, it's kind of something like this. And right, so another concept is that a spanning tree protocol, because if we have we showed that if you don't have a spanning tree structure and the physical layer has a cycle, right, so have a loop, then you will have the risk of infinite. The packet will be in the Ethernet looping forever. Okay, so we need to have a structure, build a spanning tree to avoid that. So that message is called the bridge protocol data unit, BPDU. Okay, this number is familiar. So, and it's of this shape. And if you remember, we have this priority. So we want to find the smallest router ID as a root, and then we find the closest path to it. Okay, this is next hop to the root. Okay, the bridge. BPDU. Okay, just keep in mind of that. And this I have to pass quickly. And the bridge and switch, we already know the difference. Right? So, switch every port is to a host. Bridge every port is to a subnetwork. Okay? And then we will go to the network layer, and we will not go up, okay, because we haven't finished network layer yet, actually. Okay. Again, so you need to know fragmentation layer is above the session layer. Okay, session layer is 5, fragmentation is 6. Okay? This a lot of people may ignore because we don't really have these two layers in reality, right? But in the test, we do have that. Okay, because this OSI 7-layer model is very famous. We want a student to know. Okay. And so the IP layer, we have the IP, IPv6, IPv4, those kinds of things. You should know it's in the network layer, okay, not in the other layer. Okay, the IP address in IPv4 is something like this. Okay? You should know how to translate from binary to decimal, right? Okay, and you know it's 32 bits and it's a big India. Okay, you need to know it's a big India, not small India. Right? Big India means it's a number, this is the highest bit, this is the lowest bit, right? So you list the bytes like this. Okay, small India is the root. You need to know IP address is in big India format. This is very important, right? And so IP addressing and forwarding. Right? So you need to know. So we have class A, B, C. Okay, so something like this. Okay? Class A address is starting on 0. Class B is 10. Class C is 110. Right? So then let's say we can ask you some question like, how many addresses are there, IP address are there in class B? Okay, then you need to know, hey, these 2 bits are fixed, right? And we altogether have 32 bits. Right? So here we have 30 bits, right? So then how many IP addresses we can have? 2 to the power 30, okay? Because each can be 2, 0 or 1, but we have 36 that are flexible, okay? You can say these are flexible bits, right? And this is 2 to the power 30, okay? And if I ask you this, right, so it's 2 to the power 29, okay? So you need to know this, how many IP addresses are there in each class. Okay? And so there's a concept of TTL, right? So you need to know that this is time to live, right? So going beyond that, we will not allow you to continue to send it, okay? And the TTL concept is, used by traceroute, if you remember, right? Implementing traceroute, you need to know that. We might have a question asking you what is traceroute, right? So you need to know what is traceroute, okay? Like we increase TTL by 1 each time and check the next router, okay? And each time we'll send 3, this kind of probing messages. And so fragmentation is another very important concept. Right? So, but we have gone through that example. So because of time limit, we will quickly pass. Okay. This is just a fragmentation concept. Right? So basically, there's an MTU, maximum transmission unit. If your packet size is larger than that, you have to split. Okay. And how to split those details? You can review this. Maybe we will change the number a little bit, and you should still be able to work out the fragmentation details. Okay. I will just quickly finish this slide. And then you need to know the computations, right? So you need to know, for example, usually a packet length is in the number of bits, right? And our bandwidth, or we say the rate of sending, is bits per second. Right? So if you divide the length of a packet by R, it's how many seconds you need to spend to send this packet. Okay, so this concept should be clear. And so we have the router. Router has buffers, right? If you send and you have 2 coming in, 1 out, and you will pile up. Right? If you pile up to 4, then the new packet will be dropped. Okay. So there are 2 delays. One delay is a delay you spend, to put this packet on the wire. This is where we use this to compute. Right? How is the length of your packet divided by the rate you can put on the wire? It's the bandwidth. There's another delay that you need to wait for these 2 packets to be sent. Right? So this is another delay. Okay? In general, we have this formula. So the nodal passes this router. What's the processing cost? You have the nodal processing cost. You have the queuing delay. You need to wait for the others to be sent first, and then you have the transmission delay, and then you have the propagation. Okay. Propagation light speed you can ignore oftentimes. unless you are computing the Ethernet, like a minimum allowed frame size, right? And the processing unit is also very fast. Usually queuing delay and the transmission delay are the major ones. Okay? And here you should be able to answer a question like this. Let me see whether we have a lot of questions. Okay, so yeah, we can click here for demo. Let me. So these are the maths in computer network. So for example, you can. Here is a simple demo. Okay, so you can start with send stuff and the packets counts, right? And one count, one go, one count, go. This is a balanced case. Right? So you don't have things to hide up. Okay? But if you continue to increase the rate, right? And let's start. So if you continue to increase the rate, it's fine, because sending out is faster than the transmission rate. Okay, the bits per second is even faster. Okay, but what if you decrease the rate? What will happen is you spend quite some time to send stuff. Okay, so you will start to have packets piled up. If your transmission rate is really low, right? So your coming in speed is so fast, and after a while you send one packet, okay? And then you keep coming in, and after a while you send the right. And which means incoming speed is beyond outgoing speed, then you have to wait, right? And you have to wait. For example, you are sending this, you have to wait for the packet in the front to be, and you will drop a lot of packets. Okay. So this link is also in the slide. I hope it's clear. Now we can have a question like this. Right? So we will ask you questions like, for example, we have 3 packets arrive simultaneously. Right? So basically in the queue, simultaneously we have 3 packets. Okay, 1, 2, 3. But one can be immediately put onto the one. Okay, right? So in that case, let's ask you this question. Each packet L is 8-bit. Okay, right? And our transmission speed is 64 bits per second. Right? So this is rate. So sending this 8-bit will take how much? It's 8 by 64. Okay, this is the time you send. 1 by 8. Okay, 0.125. Okay? So when the first packet you want to send it, there's no delay because there's no one before you. You need to send. Okay, but this is just a delay. Delay means a queuing delay. Okay, so you still need to spend so much time to run it. Okay? Now let's look at the second packet. You need to wait for this packet to be put on the wall. Okay, so this is the time. Now let's look at the third packet. Okay, you need to after this is putting on the wall, then you start to put this. Right? So you have 2 times this time. Okay, so you should know this, right? So in the general case, let's say we have n packets. How to derive this delay? You need to have a way to compute them. Okay. So here's a simple example. Maybe we will ask you an example that is a little bit more complicated than that, so you should be able to figure out. Right? And the queuing delay, we really want to over budget our bandwidth. Right? So if your bandwidth is very close to the incoming speed, then the queuing delay will pile up. You should over budget. So this is the concept of queuing delay. And this is trace route we talked about. 3 probes, TTL1, TTL2, TTL3, because you cannot continue forward after 3 hops. Then you can detect this router, give you some message, hey, cannot be delivered to TTL. Okay, then you will know this router and how long it takes to reach this one. Okay? So this is the trace route kind of concept. We may have a small question asking what is trace route. Okay, you need to describe those things in your own language. Okay, if you have difficulty summarizing these concepts into meaningful language, you can look up how other people do that in Wikipedia, etc. Okay, so but it's pretty clear. Right? So you just get all the routers in the middle from the source to destination, and each one you will have 3 delay times, which is magical by TTL and doing things like this. Okay, and then we have the transport layer. Right, so even though we have not reached there yet, you need to know that TCP and UDP protocols in the transport layer, and TCP has a connection. Right? So UDP, there's no guarantee of delivery. Okay, so TCP has a reliable in-order delivery guarantee, and there's also the session layer. This is the 5th layer. This is fragmentation layer, the 6th layer. You need to know. Don't don't reverse them. Right? Don't think about presentation layer is below session layer. And then up is the application layer. You can do whatever you want. Okay, even like HTML, FTP, those kind of things are all in the application, including your apps, also in your phone. Okay, and finally, like a calculation question like this, you should know how to calculate that. Okay. All right, that's pretty much this review, the whole review slide. Any questions? Yeah, basically I finished this review slide, but you need to spend some time and really memorize this stuff. Okay? Because we have 18 questions for 15 minutes. So if you don't memorize them, right, so you need to look up everything, the time may come out. Okay, you may not have enough time. Okay?
And did you say that you're going to extend lab? Because I'm going to have to study all my time on this exam if I'm going to pass it, and that time is not going to be spent in the lab if it's still due.
Yeah, I just received an email from a student. I will check it and I will talk to the TA.
You want all the students to send you an email?
No. Once we extend, we will send an announcement to you guys. Okay, probably next Monday will be the deadline. Okay.
Okay.
Yeah.
All right. Thank you.
You're welcome. Yeah. For the rest of 5 minutes, it's Q&A time. Okay. Feel free to ask a question. Yeah, we are not taking attendance today because this is really for helping you pass the midterm exam. So students don't come, they're confident, that's fine. Any questions? All right, so if you have no questions,
80
yeah.
questions or 18 questions?
Which can you repeat your question again?
Did you say 80 or 18 questions
18,
on the exam?
not 80. 18, okay, 18. 80 is crazy, right? So 18, okay, so we will have 18 questions, okay, not 80.
And do you know how long we're going to get for the exam?
Can you repeat your question? Sorry.
Do you know how long we're going to get for the exam? Like, what's the time on it?
Oh, it's a 50-minute, right? So it's a regular class on Friday, okay? But for special accommodations, with some students need the special accommodations, right? So for those, we will extend the time accordingly, times 1.5, times 2, okay? So that's why we cancel the lab.
Okay, thank you.
You're welcome. Right, so it's 18 questions, not 80, okay? We don't want to, we can have 80 questions, but it's crazy.
All right. Thank you, sir. Have a great day.
Okay, you too. Let me see the chat. If there's no more questions, I will end it. Oh, will there be a scale? So when you do the exam, each question we will say how many points are for this question. Okay, so you will see that. Right? So in quiz you can see that. Okay, you'll see, hey, this is 5 points, that is 7 points. So yes, you will be able to check the answers maybe by the end of the day or the next day. Okay, so you should be able to.
No, I meant like during the actual exam, are we going to be able to, like some formats is like one question at a time, and then some is like our normal quizzes. I was just wondering.
Oh, it will be one question at a time.
Oh, okay.
Yeah, it will not be like the current quiz. It will be, you will see one at a time, but you can go to the next, go back.
Okay, so we'll be able to go back and forth.
Yeah, because of, you have, sometimes you need to have a text box and you need to type something. So if you put everything on the same page, it will be like overwhelming. You will have one question per page, so you can go back.
Okay, thank you.
Log in while we take the test.
Can you repeat your question?
You want us to log in while we take the test?
It's recommended, right? So if you, but I know that some students are not comfortable with Of course, you are doing in Canvas, you have to log in. Right? So whether you want to put your camera on, it's encouraged. But if you feel not comfortable with that, it's okay, right? Because it's
Yes,
time.
I just meant to Zoom.
Hmm?
I just meant into Zoom.
Oh, into Zoom.
Yeah, do we have to use Zoom or can we opt out and not be in a Zoom session?
I will be in a Zoom session. If you want to ask questions, feel free to drop into Zoom, but it's not required because it will be timed, right? So it's the beginning of the class, it will start ticking, okay? And the end of the class, it will end. If you are not answering the question, whether you are in the Zoom or not, you know, but basically it's not mandatory, okay? So if you have a question, you can drop in the Zoom and we will answer the question, okay?
Do you have a practice exam or exam from a previous semester that you can share with us?
So basically, so we have the quiz, right? So you just do all the quiz, since you'll be fine. And very, very importantly, you need to review this slide. Okay, we don't share right now. We don't share the prior exam questions because we already narrowed down all the questions to this slide in some sense. Okay, maybe prior exam questions are irrelevant to what we're testing, right? So then it's not helpful. Okay.
Have you already posted these review slides?
Yeah, it's in the Canvas. Okay, the Canvas dynamic syllabus last item. You can find this stuff. Okay. All right, so it seems like no more question. I will disconnect. Feel free to send me email. Yeah. Have a nice day.